Hello. Hi. Okay, we're going to start the final session. So I'm pleased to give you a short introduction to someone who doesn't really need one, Chris Manning. Chris is a professor of linguistics and computer science at Stanford University, where he completed his PhD. And he's known for his broad contributions across statistical NLP. He wrote the seminal textbook on statistical NLP with Henrik Schutz, as well as one of the most used textbooks in information retrieval. Along with his group, he's contributed many papers to top-tier conferences across the world, as well as useful tools that we know and love if you have ever had to parse data, like Core NLP. Chris, with his students, has also been one of the driving influences for the revival and interest in deep learning or neural network methods in the NLP community through papers, tutorials, and it's actually through him and Richard and Yoshua's tutorial at EMNLP a few years ago that I got into this field. So it's had an impact on my life. So today we're delighted to have him as the final invited talk of the conference, where he's going to tell us about how neural networks can move from just predicting but also reason. So please join me in welcoming Chris to the stage. Thank you.
Okay, thank you so much, Ed. I was a little bit afraid that by Thursday afternoon there wouldn't be too many people here, but it seems like this conference is just proving to be a great success all around. So today, I'm actually not going to talk so much about natural language processing, and instead what I want to do is discuss how we might design neural networks to do higher level cognition, that is reasoning. And this talk mainly covers work done together with my student Drew Hudson. Our current neural network machine learning systems excel on a wide variety of tasks, such as speech recognition, various computer vision tasks, and they've even been pushed with surprising success to tasks in areas like robotics and natural language processing, such as machine translation. But nevertheless, by and large, these successes are in the same overall area, that the successes are in places where we have these kind of stimulus response tasks, that a stimulus comes in and we process it to recognize something or to translate it or whatever. And these are tasks that are intuitive or instinctive for humans. They aren't tasks that require careful, deliberate thinking. So the question then is, what about if we'd like to have artificial intelligence systems that can be used for reasoning? What about tasks that require more deliberate, conscious, and explicit thought? Arguably, in the early decades of AI, these were actually the kind of tasks that people thought about most. So those might be a reading comprehension task, but not one like some of our current question answering tasks, but instead ones like a middle school reading comprehension task, where you actually have to understand the interactions and relations between the characters and events. Doing common sense reasoning and problem solving. Making explicit plans for a series of actions. Or playing games that aren't like Atari games, but are the kind of strategic board games that many of us like in our spare time. For tasks like these, we really need reasoning or inference. And so then the question is, what exactly is reasoning? Well, if you're going to ask the question of what is reasoning, and the answer that you're going to give is neural networks, a really good place to start is to look at the paper by Leon Bottou from 2011, right back in the early days of the current deep learning era. So Bottou discussed how we could enhance deep learning systems with reasoning capabilities from the ground up. So he suggested that a good definition of reasoning was algebraically manipulating previously acquired knowledge in order to answer a new question. He says that Well, he points out that, often when people say reasoning, their mind immediately jumps to logical inferences, but it doesn't necessarily have to be achieved by logical inferences. In particular, he suggested that there's a kind of continuity between the algebraically rich systems that you have in neural networks over to the kind of algebras that are used in places like logic. And so that if we could start down the road of connecting together trainable learning systems in the neural network world, that might lead us on the path to inference. But in particular, what he wanted to emphasize is that central to reasoning is having a system with composition rules so that we can guide the combinations of modules in a way that we can recombine information to do new inferences, recombine modules so that we can address new tasks. And so what I'd like to talk about today is some ideas as to how we might be able to make further progress along this road to having reasoning done by neural networks. Now, at the moment, the dominant viewpoint in the deep learning community is to seek a learning device that is as empty as possible. The emptiness of the learning device is by and large compensated for by providing enormous amounts of training data to the system. And then often what people try to do is improve performance further by guiding how the device generalizes by the technique of data augmentation, which is effectively externalizing the desired inductive bias of your system in additional artificially generated training data. However, I feel that we should not be afraid of good inductive biases. Indeed, I think they're the key to producing good machine learners, ones which are capable of learning quickly and effectively. Indeed, if we look at what's been happening in deep learning, that I think most of the biggest breakthroughs in deep learning have come from building the right kind of inductive biases into models. We can certainly fail by using models with much too rigid structure, but we can succeed through the use of appropriate but flexible structural priors built into our models as inductive bias. These successes include the early success of convolutional neural networks, the development of attention, and also the kind of sequential and vertical gating that's used in LSTM for get gates and highway networks, all very effective structural biases. In most of my early work in using deep learning, I was a strong proponent of tree-structured compositional models. I believe that they really give the right inductive bias for capturing the structure of human languages. But not only human languages, there are lots of other places as well and different problems where having a tree structure is a very natural and good inductive bias. And so these kind of models in the generic terms work so that they take two vectors, initially word vectors, and build up a vector representation for the phrase. And crucially, that vector representation for the phrase was represented in exactly the same space. And therefore, that means this computational unit could be applied recursively to build up structures for larger sentences. The result of this composition captures how languages have nested phrases where the sentence meaning of the whole can be derived by composing together the meanings of the parts. As in this sentiment analysis example, the sentence starts off negative, there are slow and repetitive parts, but then it turns positive, but it has just enough spice to keep it interesting. And the tree-structured model can understand this structure and understand that the whole sentiment for the sentence turns positive. Actually, what Leon Batu proposed was using exactly the same kind of tree RNN structure for reasoning. He proposed that the path to universal composition was an association model A that maps two representations into a new one of exactly the same type. And then that was augmented by a scoring module R, which is used to guide inference, the way in which you choose to combine together your initial axioms and your derived facts. And the result of using this kind of same composition module is that you would build up a proof tree. Now, on problems with unambiguous compositional structure, an inductive bias of tree structure really does win. And indeed, there are at least a couple of papers that have been presented at ICLEAR which shows that. So one of them is on computer language program translation, and a second one by Ed and colleagues who introduced me, looking at whether neural networks can understand logical entailment. These are clear formal problems with tree structure, and in both cases you got big advantages from using a tree-structured model over something with a simpler inductive bias. However, on the other hand, in my own field of natural language processing, it's proven really challenging to get sustained gains in NLP task performance from using tree-structured models. For various reasons, including the fact that tree-structured models are very GPU-unfriendly compared to simpler models, but also because of their use of symbolic tree structure where you're making hard decisions, and the sensitivity to parse errors, which is very easy to make with natural languages, it's been hard to get gains. So in this work, I actually want to pursue a different path to how we might approach compositional reasoning. It's possible to have compositional reasoning without trees. One alternative is to use an attention model inside a sequential model. Now, in a way, you could say this is almost trees by another name, since effectively attention gives us for free n-ary operations where we can feed in all the preceding nodes into our composition unit. But we still get the advantage that we have now soft weights on the different preceding nodes to decide how much to use these auxiliary arguments, and so this is a more flexible and more easily optimizable setup. But it's possible that we don't even actually have to do that. And in fact, the results that we have in the systems that I'll show later suggest that. So a second alternative is to think that maybe our sequential neural networks can essentially do what logicians call currying. So it's an elementary observation of logics that if you have a multi-argument function, f of x, y, z, you can always transform it into another function, the curried function, where it takes one argument and then it returns a function which will take an argument and return yet another function which takes the third argument and then will give you your result. And it's perhaps reasonable to assume that we can use sequence models to do precisely this kind of computation, taking arguments one at a time. Okay, so what is our goal in this work? So in this work, Drew and my goal is then to say, well, at the moment, the vast majority of machine learning, it's building these big correlation engines where you're learning any kind of association between what's in the input data and the results that you want to assign. We'd like to have a different kind of neural network design where it explicitly has a structural prior that encourages compositional and transparent multi-step reasoning. But on the other hand, we'd like to avoid the issues with something like tree recursive neural networks and to have a model that maintains end-to-end differentiability and is easily scalable to real-world problems. Okay, so this is the outline of the rest of my talk. So the first part of it explained the desire to move from machine learning to machine reasoning. So I hope you were all convinced by that. So then in this next bit, I'm going to explain a little bit about the clever task, which is what I'll provide experimental results on today. Then there'll be a big main part talking about the model that we're proposing, memory attention composition networks, or MACNets, and then I'll go on and show some experiments and discussions about that. Okay, so the task that I'm going to be looking at today as a concrete task is this clever data set. So it's an artificial visual question answering data set that was made by Justin Johnson while he was interning at Facebook AI Research. So here's an example of an image and a question. There is a purple cube that's behind a metal object left to a large ball. What material is the cube? So these questions have the kind of complex compositional questions which are custom designed to be good places to see whether you can understand and reason. So if we just walk through for a moment what you have to do, you start with there being a purple cube, so there are a couple of purple cubes. Then it says it's behind a metal object, so there's a metal object and the things behind it. Then left to a large ball, so there's a large ball and the things left to it, so that pretty much narrows it down to a certain purple cube. And then it asks, what material is the cube? And you probably think, gosh, I don't know, what material is that? But it turns out in the Clever data set, there are only two materials. Things are either metal or rubber. So if they're not shiny, they're rubber. And so the answer is that this is rubber. So that's the main setup of the problem, but something that's important to note that's down the right-hand column is each instance in Clever is accompanied by a functional program, which is sort of, you can think of it kind of like a database query that specifies various filter and select and relation operations, which will compute the answer to the question. And that's important because some of the other models that we'll look at make use of that data. Okay, so the Clever data set, it's another of these sort of artificial generated data sets. It's not a real problem in the world. So starting off on the visual side, these are photorealistic images of 3D objects in a few shapes, colors, materials, and sizes. They're actually all made in Blender, if you have kids that use Blender. It's accompanied by these highly compositional multi-step questions which seem good for assessing reasoning. And then, as I mentioned, there are these tree-structured functional program representations. So it's actually the case that the language of the questions also isn't really natural language. The language of the questions is actually generated from these functional program representations by rule. So actually in the basic version of Clever, we don't actually have a natural language understanding task. We have artificial controlled language understanding task. Nevertheless, it requires a variety of reasoning skills such as transitive inference, counting, and comparison between attributes and amounts. And, to make my natural language processing self a bit happier, alongside the Clever data set, there is then the Clever Humans data set, which then does have genuine human-asked questions collected from mechanical Turkers. But the strengths of Clever are, well, by the construction of the data set, it allows thorough analysis of performance based on the question's structure and type. But more particularly, part of why it was originally designed was there was this first generation of visual question answering work, and it looked impressive initially, and then people started to discover that there are a lot of question conditional biases and opportunities to do spurious and superficial reasoning. So it seemed that most of the initial VQA systems didn't actually understand much about either language or the images. So you got things like if the question was asking what covered the ground, you didn't have to look at the image, the answer was always snow. And so Clever was put together precisely so that would not be the case, and that you actually had to understand the language and the picture in able to be able to answer them correctly. There's been a number of previous pieces of work that have already looked at the Clever data set. They basically fall into two groups. So the first group is the neural module network approaches. So these were pioneered by Jacob Andreas and colleagues, and there's also been an approach pursued by Justin and Johnson and colleagues. And essentially, these models treat it like a semantic parsing problem in NLP terms. So all of these models make use of the strong supervision that comes from the functional program. And so what you're doing is a two-stage operation. The first stage is that you use a sequence-to-sequence model to translate the English form text back into the functional program using the strong supervision. And then the second phase is actually the neural module network, where you use the functional program to piece together custom neural network pieces. So there's a discrete collection of specialized neural modules for doing things like selecting, filtering, counting, comparing, and they're stitched together based on the functional program, and then they run. More recently, there have then been a new class of models which don't use the strong supervision, and essentially they are large ConvNet stacks interleaved with some kind of specialized layer. So the first such system was the relation nets done at DeepMind, and the relation net layer that's stuck in between the convolutional layers takes every pair of pixels in the image and considers a relation between them and makes predictions based on those binary relations. And then more recently, again, from the University of Montreal, is the film system. And it also sticks layers inside the convolutional network stack. But this time they're kind of like a controllable normalization layer where the processing of the question tilts the normalization that happens between the layers. It's a little bit harder to get an intuitive sense as to why that's a useful thing to do, but it is. Okay, but now what I want to do is move on and tell you about the memory attention composition networks that we've designed. So the idea of this network is how could we custom design from the ground up a neural model which has a better structural prior for problem solving and reasoning tasks. And building on the success of sequential models, that this model is explicitly a sequence model, but it's designed to be more constrained in such a way as it encourages it to do a sequence of explicit reasoning steps, each of which is performed by a MAC cell, a memory attention composition cell. So in particular, as a recurrent network, there's one universal MAC cell that is used throughout all the steps. But its parameterized design is such that it's versatile and it can adapt its behavior and context to perform different operations. So we don't need kind of custom networks for every different kind of reasoning operation that we want to do. This network will then make use of self-attention, so it can actually simulate arbitrarily complex reasoning graphs using self-attention while maintaining end-to-end differentiability. Okay, so we'll then, for the next few slides, gradually work down into the details. So for a single MAC cell, it's meant to do one reasoning step. And to do that, it makes use of having two recurrent states. So we have a control state, and so this represents the step's reasoning operation. And the reasoning operation is going to be represented as an attention-based average of a given query, where the query for Clever is going to be the question that we're asked. And then we also have a memory state. So the memory is going to store retrieved information that's relevant to a query and can be accumulated over steps. And so it's actually also going to be represented as an attention-based average, but it's going to be an attention-based average over what in general I'd like to suggest is the knowledge base. But for the work I'm presenting here on Clever, our knowledge base for answering questions is simply looking at an image. Before we get into the details of the MAC cell, we need to have a knowledge base and a query to feed into the MAC sequence. And there is a pre-processing layer that uses pretty standard methods of neural network pre-processing. So for the query, it's processed by BioSTM, and that yields a sequence of contextual words, the hidden layer of the BioSTM, and an overall query representation that's formed in the standard way by concatenating the final forward and backward hidden states. For our so-called knowledge base, that is the image, we're using a completely standard ResNet stack. Indeed, we're using the one that Justin Johnson made, and then using the output of that as our knowledge base representation. So in slightly more detail, here's the picture for the MacNet. And so the first thing to notice is that it has two recurrent states. It has a control state and a memory state. And so there is a fundamental idea here, which is to think maybe there's actually something good in the kind of architecture that's been used throughout the history of computing, where control and memory are separated from each other. At any rate, that's a hypothesis that's being developed in this work. So the control unit computes a next control state, extracting an instruction from the query. Then the read unit retrieves information from the knowledge base, given both the previous memory, it's again working recurrently, and the current control. And then finally, the write unit is going to update and write the next memory, merging the newly found information with the previous memory to then write the next memory. So quickly, in one more level of detail, though this is probably getting to be slightly more detail than you could absorb off PowerPoint slides, but I'll just sort of say a minute or two about how we get down into the details of what things do. Okay, so this is the control unit. So the control unit has as its inputs the previous control state, the query that's the summary of the query to perform, and the contextual words. And so first of all, it calculates a time-specific query representation through a linear layer. Then it combines that with the preceding control instruction. And then at that point, it uses a particular architecture which we both thought would be very useful for interpretability and proved to be very successful performance-wise, which is our calculated representation, CQI here, is projected down onto the actual words of the query. And the way that that's done is in the standard kind of attention way. So we put an attention distribution over the words of the query, and then we calculate a weighted average of those words. The read unit is the most complex part of the system. So it takes the previous memory and the knowledge base. So first of all, it's going to be considering each item in the knowledge base, which is sort of the outputs of the conv filters. And first of all, it considers relating them together with the previous memory. So this is a facility that makes it easy to do transitive reasoning, because the preceding memory can guide you to what to get next from the knowledge base to reason transitively. But we don't only want to do transitive reasoning. Sometimes we'd like to be able to combine multiple memories together, such as when we do logical operations like OR and or counting. So we again combine the output of that with accessing over the memory. Then we also want to consider what to do based on the control that we've calculated. So the control feeds in, again, doing a Hadamard product, and then at the end of that, we're again doing a projection via attention back onto the knowledge base items, and this attention weighted average then becomes our candidate new memory that we pass forward. And then there's the write unit. We actually explored a couple of write units of more or less complexity. The simplest write unit is you take your newly calculated memory and your previous memory, and you put it through a linear layer, and you write it as your new memory. And it turns out that actually works pretty well. But you might think that sometimes you've got to do a hard amount of thinking and sometimes only a little bit of thinking. So it might be useful to have a highway gate so that once you've finished your reasoning, you can just easily pass through your preceding memory. Or we had this idea of using self-attention, where you could use all of your memories to help guide the next memory. And so we could put in a self-attention layer so we can make an explicit DAG of inference steps. So concretely, the way we do this is we then use a kind of a key value memory network idea, so that we're taking the attention distribution between preceding control states and using that to access preceding memories. Okay, so that's our MAC network, our MAC cell, and the way we make our whole MAC network is then just using these recurrently, and in particular allowing it to be directed acyclic graph using attention. So this gives us a fully differentiable end-to-end model for reasoning. The final bit we have to have is network outputs. This is actually very easy for Clever. There are actually only 28 possible answers. There's yes, no, there's colors, materials, comparisons. There are numbers, but all of the numbers are single digits. There are only actually 28 answers, and so we simply use a 28-way softmax. And so this takes in both the memory and the final form of the query. Using the query at this point is vital because of the way that the MACnet segregates the query from the memory, that the memory does not really represent the query and it has to be combined in again. Okay, so here are some of the experimental results and a bit of discussion. So in the Clever data set, overall there are 700,000 training examples, 150,000 test examples, the 28 answers. Because there are a limited space of answers, the baseline is very small. There are lots of yes-no questions or metal versus rubber questions. And so if you guess the most frequent answer for each question type, that gets you to 41%. Using ConvNets and LSTMs is sort of the standard baseline VQA architecture. That does a bit better, but not a lot better. That gets you 52%. Jacob Andreas's initial neural module network work did a lot better than that. That got you to 83.7%, which seemed to be heading in the same direction of some of these tasks where you were kind of closing in on what was measured in the original paper as the performance of humans, which was 92.6%. But remember that this is a completely artificial and task with artificially constructed language and deterministic answers. So there's actually no reason for this task why you shouldn't be able to get 100% right. And actually there's a bogus reason why the humans tend to perform a bit imperfectly, which if someone wants to ask, I can explain later. So because of that, actually in recent work, all of the action has moved to the 95 to 100% level. And so that started with DeepMind's relation networks, which got just over 95%. Justin Johnson's second-generation neural module networks get 96.9%. Film got 97.7%. And you're probably expecting that it turns out the MACnet does better again, getting 98.9%, more than halving the previous error rate. But nevertheless, these numbers are getting so high, you might be sort of suspicious as to how much signal there is there. I think there is signal, but maybe it's more interesting to look at some of the details. So in basic Clever, there are 5 kinds of questions. There are existence questions, does something exist? There's querying an attribute and comparing attributes between two things. And all of these 4 systems get over 97% on all of those. The harder kinds of questions are the ones that involve numbers, comparing numbers and counting. And so in particular, previous systems had the most difficulties with counting questions. So both the relation networks and the second-generation neural module networks got about 90% on the counting questions. Film did rather better, and then MACnet is doing a lot better again on counting questions. But even for MACnet, the class of examples it does least well in is counting questions. And this might make you wonder whether having more of a counting primitive would actually be also a useful kind of structural prior to consider putting into a reasoning system. Here are a couple of more interesting results. So how fast do these models train? That's a good reflection of whether they have good inductive biases. Trying to use LSTM plus CNN plus spatial attention model, it learns very slowly. That's the bottom line. Film and the second generation neural module networks are better again, but MacNet trains much faster again. So in 2 epochs through the data, it's performing as well as the neural module networks are performing after 10 epochs through the data. And I think you can take that as stronger evidence that this model does just have good inductive biases that help it to learn. Here's another demonstration of this looking at a learning curve by restricting the amount of data that you train on. So if you train on 700,000 examples, several of the models do very well indeed. But if instead you say, let's just train on 70,000 examples, 1/10 of the data set, what you then find is all of the other good approaches like film and Justin Johnson's neural module networks are getting at most 51.6%. Again, not really that much more than the 42% baseline. Whereas Mac is still doing really well. Even 70K examples is enough for it to get 86% correct. Then here's our real human language, the Clever Humans data set. So it consists of 18,000, a small number of real human language examples coming from crowdsourcing. So the humans were instructed to write questions that would be hard for a smart robot to answer. In particular, they were able to ask any kind of question which could be semantically quite different to the only 5 types that the systems were trained on. That data set was regarded as too small to actually train on. So the first thing people have done is just a blind transfer task, and here are the results from that. And then the second thing is that there is a corresponding dev set or adaptation data set for Clever Humans. So people will then adapt on that data set and then see how well you do. And so if you do that, what you notice is, well, not only does MacNet win again, but MacNet is actually gaining differentially more in doing the adaptation, which again I think reflects the fact that it has good inductive biases, so it can generalize much more quickly on that data. Okay, here are a couple of pictures. Because of the fact that the model uses attention both to the query and the knowledge base, you can have a fairly concrete idea of what the model is doing. So this question is, what color is the matte thing to the right of the sphere in front of the teeny blue block? Now, for the length of the sequence model, you get the best results by running it with a reasonable length sequence model of running it with a length of somewhere between 8 and 16. But for showing pictures, it's better to have a shorter sequence model, and it still performs fairly well with the short sequence model. So what we find is for the first time period, it focuses in the language on teeny blue block, and it finds the teeny blue block in the picture. Then it focuses on the sphere in front of, and it finds the sphere in front of, and then it says what color is the matte, and it focuses on the what color is the matte, and it answers it correctly and gives the answer purple. Here's a more complex and harder to see example. How many objects are either small objects behind the teeny metal cylinder or metallic cubes in front of the large green metal object? I can barely read this myself. Interestingly, what you notice here, and this is quite common in the way it behaves, is it'll then, with a longer sequence model, it'll use the first couple of steps to absorb semantics. So at first it's focusing on how many and small, then it's focusing on the fact that this has a disjunction in the condition, and then it starts looking at large green metal object, and looking for metal cubes in front of that. And you can see there it's found the large green metal object, and it's then looking for the metallic cube in front of that. And then it moves back to the first half, the teeny metal cylinder, and then looking for small objects behind that. And at time step 5 is finding the teeny metal cylinder and then the small objects behind that. And so this is actually enough information that it can successfully count, and it gives the right answer of 4. Here are a couple of clever human examples, just one off, which sort of show the different kind of semantics of questions that's being asked in clever humans. So what is the shape of the large item mostly occluded by the metallic cube? What color is the object that's a different size? What color ball is close to the small purple cylinder? So we've got notions like occlusion and close to that were nowhere in the original semantics. Okay, so I hope to have shown to you that this works pretty well. Let me just quickly emphasize, how does this differ between MAC nets versus module networks? So neural module networks are also an architecture that speaks to Leon Batou's vision, that they're also composing together pieces to do more complex inferences. But I think this model is advantageous because we're making use of one universal and versatile cell that's used across all states, sharing architecture and parameters. And indeed, we did some ablation studies. You actually get worse performance if you don't share the parameters in a sequence model manner. But this cell can adapt its behavior based on the context in which it's applied. In contrast, the neural module networks have a discrete fixed inventory of really rather task-specifically designed specialized modules with distinct parameters and even architectures. So they lack the generality and they lack any of this concept of sharing and universality. Against the Phil model for Montreal, we actually did take a key insight from the Phil model. So the Phil model proposed a model in which, rather than transforming both the query and the knowledge base into the same representation, it proposed an indirect modulation. And we've sort of borrowed that kind of indirect modulation. But I think we really benefit from having our close attention to the query and the knowledge base, where Phil's conditional normalization layer is kind of a global tilt which is applied identically across all image reasons and doesn't allow the kind of selective behavior based on features or positions. Okay, so I hope that I've shown you this idea that maybe there are interesting things we could do to push neural networks to do higher level inference and reasoning, to get back to what artificial intelligence was meant to be about, where we would have thinking going on in our neural network architectures. I've proposed a particular design for doing that, which is a form of constrained sequence model separating control and memory, and particularly exploiting attention as a good model for reasoning. And I've argued that it has strong compositional reasoning skills and the right kind of inductive bias to be able to do well in these kind of tasks. And it's practical as a generic, fully differentiable end-to-end model. Now, is this the one and only true answer as to how you could design a neural network more for reasoning? I'm sure it is not. I'm sure there are lots of other ways and variants that people could think of exploring. But I think it is an interesting challenge for the community to actually be putting more effort to be thinking about what are a few more different and good building blocks that we could be using in neural net architectures rather than being so dependent on such a very small vocabulary of ideas as so much of the work in the field has been in recent years. Thank you.
Okay, we have time for some questions. Dimitri?
Thank you. Great work. It's an interesting idea to separate control and memory, but then what happens is that you decide which steps of reasoning will be performed regardless of what result from the knowledge base the previous steps of reasoning fetched. So you decide in advance what reasoning you'll do, and you don't look at what you retrieve. Do you think this has some limitations?
So that's a great question. So I actually think that you're pinpointing one of the deficiencies of this current architecture. So it seems like a key thing that you'd like to be able to do for reasoning in general is you're searching your knowledge base, You've discovered that a person was born in Poland, and therefore you say, okay, well, I'm going to take that fact and incorporate that and start looking for other people in Poland that they might know, or whatever it is. So you want to have the memory feeding back into the control to determine future actions. And I think absolutely that's true, and that's something that should be incorporated into a MacNet version 2. It sort of happens that for the particular design of Clever, you don't have to do that because you are really sort of following the instructions that's in the question. But, I think that's a key avenue that's a deficiency that should be addressed in the future.
Thank you.
I think we have time for at least another question.
There's a lot of work on making neural networks explainable or interpretable, and it seems like in reasoning, it's important not to just get an answer, but also why did it give that answer? Do you have any thoughts on making it more interpretable or explainable?
Okay, partly not. So it was actually one of the hopes in the design of this architecture that it would be a model that was transparent, interpretable, and explainable. And that was initially a motivation for grounding both halves of the model as doing attention distributions over the query and the knowledge base. And it was really kind of then a lucky side effect that we found that actually improved the speed of learning and improved performance as well. So in one sense, there are these lovely attention pictures that I can show you which makes things kind of interpretable. But on the other hand, as a lot of us know who've looked at attention pictures, it's kind of easy to tell just so stories about them, and you can never be quite so confident as exactly what it means as to what the thing is doing. You can show that there's good localization over time, but it's hard to tell whether it's really computing in back of or doing greater than. And so I think there's sort of more work to be done for that. I'm not sure I have a specific answer to that, but clearly various ideas people are starting to explore, such as generating text alongside the models to have them explain what they're doing.
I'm afraid that's all we have time for, but let's thank Chris again for his keynote.
Thank you.